There are approximately 3.04 trillion trees on this planet. They grow on every continent except Antarctica. They self-replicate. They absorb carbon dioxide as they grow. They require no factory, no mining operation, and no supply chain. And in 2021, 3 independent research teams proved that the cellulose inside these trees can generate electricity when compressed. Conduct ions faster than any polymer ever tested, and form the structural basis of electronic circuits that biodegrade in soil. 3 trillion trees, each one producing cellulose every day of its life. The raw material for the next generation of batteries, sensors, and building materials is not buried underground. It is growing above it in unlimited quantities. For free. This is not a theory. This is not a concept paper. This is peer-reviewed, published, replicated research from 3 of the most respected scientific institutions on Earth. And the fact that you are hearing about it for the first time right now tells you everything you need to know about who controls the future of technology and why. Let us start with the most fundamental discovery. Wood has a natural piezoelectric effect. That means when you compress it, it generates a small electrical voltage. Scientists have known this for decades, but the voltage was so tiny, so negligible, that nobody took it seriously. It was treated as a scientific curiosity, a footnote in a materials science textbook, something you acknowledge, document, and move on from. Then in 2021, a team at ETH Zurich in Switzerland, one of the top 10 research universities on Earth, decided not to move on. Professor Ingo Bergert and doctoral researcher Jiang Wo-sun wanted to know what would happen if they made wood more compressible, not by crushing it with brute force, but by changing its internal chemistry. Wood cell walls are made of 3 substances: cellulose, which provides structure, hemicellulose, which provides flexibility, and lignin, which acts as a rigid glue holding everything together. Lignin is the reason trees can grow tall. It prevents the cellulose fibers from buckling under their own weight. It is the skeleton of wood at a microscopic level. Bergert's team placed blocks of balsa wood into a simple bath of hydrogen peroxide and acetic acid. Both chemicals are common, inexpensive, and widely available. The acid dissolved the lignin, leaving behind a white, spongy framework of pure cellulose layers. The wood went from a rigid block to a soft, compressible sponge, but it retained its internal architecture. The layers of cellulose remained aligned, intact, and organized exactly as they had been inside the living tree. When they compressed this delignified wood sponge and released it, something remarkable happened. It generated an electrical voltage 85 times higher than untreated wood, not 8.5% higher, not twice as high, 85 times. The sponge could be compressed and released hundreds of times without degradation. They ran 600 consecutive load cycles on a test cube with a side length of just 1.5 centimeters. The voltage remained stable throughout, approximately 0.63 volts per compression. Consistent, reliable, repeatable. Then they scaled it. They connected 30 of these small wood blocks together and applied the body weight of a single adult. The combined output was enough to power an LCD display, from wood, from footsteps, from a material that grows in sunlight and decomposes in soil. The results were published in Ax Nano, one of the most respected nanotechnology journals in the world, and the team did not stop there. In a follow-up study published in Science Advances, the researchers asked whether they could achieve the same delignification without any chemicals at all. They found the answer in a fungus called Ganoderma applanatum. This organism causes what is known as white rot in wood. It selectively breaks down lignin and hemicellulose, while leaving the cellulose structure largely intact. In other words, nature had already invented the process. The fungus does exactly what the acid bath does, just more slowly and with zero chemical waste. The fungal treated would produce lower voltage than the chemically treated version in initial tests, but the process was entirely biological. No hydrogen peroxide, no acetic acid, just a fungus and a block of wood. Professor Bergert described the potential applications clearly: sustainable building materials that harvest energy during their use phase, skin-friendly biosensors for medical applications, flooring that generates electricity from foot traffic. Imagine a hallway in a hospital, a school, or an airport, where every footstep powers the sensors and lighting embedded in the building itself. The material is biodegradable. The process is simple. The raw material is the most abundant structural polymer on the planet. Cellulose is not rare. It is the single most common organic compound on Earth. Now, if the piezoelectric wood was the only breakthrough, it would already be significant. But it was not alone. In the same year, a completely separate team published a completely separate finding that makes the ETH Zurich discovery look like the opening act. Professor Liang Bing, who at the University of Maryland had been studying wood for years, in 2018, his team made international headlines by creating what they called The process was conceptually simple. Remove the lignin from a block of natural hardwood, then compress the remaining cellulose structure under heat. The result was a densified material that was 12 times stronger than natural wood and 10 times tougher, stronger than titanium alloy at a fraction of the weight. A bullet fired at a sheet of superwood could not penetrate it. The research was published and broadly covered. Who was invited to showcase the material at the White House? But it was his 2021 paper that changed everything. Working with colleagues at Brown University, whose team took cellulose nanofibrils, the tiny polymer tubes found inside wood fibers, and combined them with copper ions. The resulting material was paper-thin, flexible, and could bend without breaking. But its most extraordinary property was conductivity. The wood-derived cellulose conductor moved lithium ions at a rate 10 to 100 times faster than any polymer ion conductor ever recorded. 100 times, not a modest improvement, a generational leap. To understand why this matters, you need to understand what is inside every lithium-ion battery on Earth. Between the two electrodes sits a substance called the electrolyte. Its job is to carry lithium ions back and forth as the battery charges and discharges. In virtually every commercial battery today, this electrolyte is a liquid made from volatile, flammable, organic solvents. It is the reason batteries catch fire when punctured. It is the reason phones explode. It is the reason every lithium battery must be handled, stored, and transported according to hazardous materials regulations. Scientists have been trying to develop a solid electrolyte to replace this liquid for decades. Ceramics work well as ion conductors, but they are brittle. They crack under the stress of repeated charging cycles. Polymers are flexible, but they conduct ions poorly. For 30 years, this trade-off appeared unsolvable: flexible or conductive. Pick one, whose cellulose conductor was both. Flexible enough to tolerate repeated cycling, conductive enough to match ceramics. And it came from a tree. The paper was published in Nature. Not a specialty journal, not a regional publication. Nature, the single most cited, most rigorous, most prestigious scientific journal on Earth. The peer reviewers confirmed the data. The conductivity numbers held, and the implications were stated plainly by the authors. This material could serve as a solid electrolyte for next-generation lithium metal batteries, the type of battery that could double or triple the range of electric vehicles while eliminating the fire risk entirely. Co-author Yuki put it simply: using materials nature provides will reduce the overall impact of battery manufacture to our environment. Now hold these two discoveries in your mind simultaneously. ETH Zurich proved that processed wood generates electricity from compression. The University of Maryland and Brown University proved that processed wood conducts ions better than any polymer in history. Both published in 2021, both peer-reviewed at the highest level, both using cellulose, the most abundant organic polymer on the planet, derived from trees that grow on every inhabited continent. And then came the third breakthrough. At EMPA, the Swiss Federal Laboratories for Materials, Science and Technology, researchers working on the European Union's Hypea Lignum project developed a fully functional printed circuit board made entirely from wood-derived biomaterial. Not a concept, not a rendering, a working circuit board. They built a computer mouse with it to demonstrate that the material could handle real electronic components, real soldering, and real data transmission. When the device reached the end of its life, the substrate biodegraded, it composted, it returned to soil. This matters because the electronics industry currently produces 62 million tons of electronic waste every single year. That number was confirmed by the Global E-Waste Monitor in 2024. Of that 62 million tons, less than 22% is formally recycled. The rest is dumped, burned, or shipped to developing nations, where children and informal workers disassemble it by hand, breathing in lead, mercury, and cadmium fumes. The circuit boards inside your phone, your laptop, your television contain epoxy resins reinforced with fiberglass and laced with brominated flame retardants. These materials do not biodegrade. They persist in landfills and waterways for centuries. IMPA proved that a wood-based substrate can do the same job, and when it is finished doing that job, it disappears into the earth. 3 institutions. 3 discoveries. Wood generates electricity. Wood conducts ions at record speeds. Wood replaces toxic circuit boards. All published between 2021 and 2025. All using the same base material. All peer-reviewed in top-tier journals. The convergence is so overwhelming that it seems almost impossible for it to be ignored. And yet, the global metals and mining industry recorded revenues of approximately $3.5 trillion in 2023. The lithium-ion battery market exceeded $150 billion in 2025. The circuit board materials market generates tens of billions more annually. These industries rely on supply chains that stretch across continents, that require massive capital investment in extraction infrastructure, that employ millions of people in mining operations from Chile to the Congo. In the Democratic Republic of Congo, children as young as 6 crawl into artisanal cobalt mines to extract the material that goes into your batteries. Cathode, they earn less than $2 a day. They work without protective equipment. They breathe metallic dust that causes fatal lung disease. International human rights organizations have documented this for over a decade. The supply chain continues because the demand continues, because every lithium battery needs cobalt, because every phone, laptop, electric car, and grid storage system on Earth currently depends on materials ripped from the ground by the most vulnerable people on the planet. Wood does not require child labor. Wood does not require open-pit mines. Wood does not leach heavy metals into groundwater. Wood does not explode when punctured. Wood sequesters carbon dioxide while it grows and biodegrades harmlessly when it is discarded. The question is not whether wood-based technology works. ETH Zurich, Brown University, the University of Maryland, and IMPA have already answered that question definitively. It works. The data is public. The papers are accessible. The methods are replicable. The question is why a technology that is cheaper, safer, renewable, biodegradable, and scientifically validated at the highest level has not displaced even a fraction of the mining and chemical-dependent supply chains it could replace. And there is one company that suggests the answer might be simpler than a conspiracy. It might just be inertia, money, and time. Inventwood, a startup founded to commercialize Professor, whose superwood technology began construction of a 90,000 square foot manufacturing facility and achieved its commercial launch in 2025. The material is real, it is being produced, but it took 7 years from whose initial publication to the first commercial batch. 7 years of fundraising, engineering, regulatory navigation, and market development. For a material that is objectively superior to the metals it replaces, 7 years is not a long time in the history of materials science, but it is a very long time when 62 million tons of toxic e-waste are being generated every year, when children are dying in cobalt mines every month, and when batteries are catching fire in homes and airplanes and parked cars on a weekly basis. The peer-reviewed evidence says that cellulose from trees can generate electricity, conduct ions at record speeds, replace structural metals, and form biodegradable electronics. The 3.04 trillion trees already on this planet produce this cellulose continuously, passively, using nothing but sunlight, water, and carbon dioxide. The raw material is not scarce. It is not expensive. It is not controlled by any single nation, corporation, or cartel. It grows everywhere. It always has. The barrier is not scientific. Every major claim in this video is backed by research published in Nature, Science Advances, or Axe Nano. The barrier is not technical. Working prototypes exist for piezoelectric wood floors, solid-state battery electrolytes, and biodegradable circuit boards. The barrier is not material. Cellulose is the most abundant organic polymer on Earth. The barrier is economic. A $3.5 trillion mining industry does not transition willingly to a competitor that grows in sunlight for free. A $150 billion battery industry does not abandon its liquid electrolyte supply chain because a paper in Nature says wood works better. An electronics industry, generating 62 million tons of profitable waste per year, does not voluntarily adopt a material that composts in a garden. Change does not come from the industries that profit from the status quo. It comes from the people who learn what the status quo has been hiding. 3.04 trillion trees. Every one of them is a factory. Every one of them is a power source. Every one of them is a circuit board waiting to be made. The science is settled. The material is here. The only thing missing is the decision to use it. That decision does not belong to a corporation. It does not belong to a lobbyist or a shareholder or a supply chain manager. It belongs to you.